Try that one more time. There we go. It should connect momentarily. There we go. All right. Let's see what time is it? 7:01, so we can get started. All right. So what we'll do today is to continue with the floating point number discussion. And then on Thursday, 2 days from today, I'll give you guys the practice exam for exam 1. And then next Thursday, we'll have the actual exam 1. Is that okay? So you have one, so you basically have more than a week to prepare for exam 1. The recorder is on, so it's all good. Keep in mind that the exam is going to last the entire lecture period, so you have 80 minutes. I do recommend you guys come here, on time, so that you don't lose time unnecessarily. I cannot extend the exam time, to the lab time because the lab is not even close to Rave Hall. Okay, so there's no way I can extend it. It is open book and open notes. Basically open anything that is either printed or handwritten prior to the test. And that includes any material. So you can print out the modules if you want to. You can print out the modules. You can also take screenshots of the video. If you find that a particular screen on my tablet is useful, you can just take a screenshot and put it onto paper. You can work together, okay, when you are preparing for the test, not when you're taking the test, okay? So you can work together to prepare for the test. And if you want to share notes, okay, any written notes, you can make copies prior to the test, but you are not allowed to share notes during the exam. Is that okay? So let's say 5 of you guys sit together and study, and then you guys together figure out, okay, I think this is going to be useful, this is going to be useful, let's make a key of all the key symbols and whatnot. After you make all of that material, you can make 5 copies, okay? And each one of you can bring your own copy to the exam. That is perfectly okay. Is that okay? So there's no limit on how much printed or handwritten material you can bring with you, only limited by how much space is available, in this particular Rave Hall, which is kind of limited, unfortunately. Yep. So you're right, it is kind of limited. Is that okay? Yep.
How relatable are the practice tests to the test?
I do not know yet, because I don't know what exam questions I'm going to ask for this semester. But what the practice exam is, they are actual exams of past semesters. So that would give you an idea of, oh, okay, so those were the questions from previous semesters. But since I do not ask the same question twice, so you're also guaranteed that it won't be exactly those questions. Are there any questions? Okay, go ahead.
Should we expect it to be like concepts from lecture and then...
and lab.
Okay, concepts from lecture and then like example problems like from lab like that?
Yes, but there will be problem-solving type of questions where you may not have solved those particular problems in lab. But from what you already understand about the concepts, you should be able to solve those problems in the exam. In other words, I give you, okay, this is how you get from A to B, and we'll do some exercise. This is how you get from B to C. I'll give you some exercise. This is how you get from C to D. I'll give you some exercise. So in the exam, I may ask you a question and go like, here's A. How do you get to C? So you have to link, okay? You have to link the concepts that you have already understood because of doing the lab, because of the lecture, because of reading the modules, and so on. So it's about the application of what you have learned and not really that much about the knowledge itself. It is about the application of the knowledge. And that's why it's open book and open notes. Because if you have memory like mine, which is really bad, I need to have some material so I can remember certain things, details. I have to I need some help. But in terms of applying those concepts, I should be able to do it. Yep.
Date for the exam?
Next Thursday. So it is the Thursday before the campus closes. Is that okay? So I'll give you the practice exam on Thursday or before. Okay, so I will probably make it available on a shared drive so that you guys have access to it. So each one of you can download it, print it out, write down whatever you want, and then I'll go over the answers during Thursday, during the lecture. Is that okay? So the scope is going to be up to but excluding floating point numbers. So none of the floating point number stuff is going to be in exam 1. Okay? It may sound like good news. It simply means that floating point stuff is going to be in the next exam. So I'm not really sure it's good news. So, all right. So let me go back to the exam. I mean, not the exam, but the floating point number stuff. And it is all the way up here. Floating point number representation. And I think I skipped one portion, or maybe I just ran out of time last time. I didn't have enough time to talk about it. Is the regular expression stuff. Okay? So I don't think I went through this stuff in the previous class, did I? Nope. Okay. So regular expression, this is basically saying, okay, what does a base 10 scientific notation number look like? Okay, let me highlight which portion is the regular expression. This is the regular expression. Does that by itself, verbatim, look like a number to you? No. What do you think it is describing?
The syntax.
The syntax, very good. It's describing the syntax of a base 10 scientific notation number. Is that okay? So why do we care about the syntax of something in computer science?
So we can identify what's in play.
Well, okay, for several reasons. One is, we can validate. Okay, based on this, we can validate whether a given number is in scientific notation or not. Okay. The second thing is all of these notations may come in handy at some point when you become a developer or a computer scientist in the field. How many people have heard of this term, regular expression? Let me highlight just the term itself, regular expression. Okay, in what context have you guys heard about this term? Go ahead.
Pattern matching in text.
Say,
Pattern matching in text.
okay, pattern matching. And why do you want to pattern match? What would be the application of that?
Grabbing data from a document or
Pulling data or searching for something, right? Okay, so let's say you have a list of stuff and you want to locate a particular item, but you don't know exactly what you're looking for, but you know the pattern of that. Yes, go ahead.
I was just going to mention manipulate. Oftentimes you use regular expressions to manipulate. Like, so to find the data and then to take that data, and because it's sanitized by the regular expression, you can manipulate that data and use it in the application.
Right. Or if something does not match the expected regular expression, then you can flag the end user and go like, okay, this is not the correct date format, for instance. Okay, or this is not the correct social security number format. So that is really helpful. Okay, regular expression is really helpful all by itself. So what we'll do is we're going to use regular expression to describe what a number looks like when it is in scientific notation. This is all in base 10, okay? The reason why this is actually important is because in one of the ungraded assignment, I want you to write the program to parse regular expression, not regular expression. I want you to parse a scientific notation so that you can have a basis to start with, and then we will eventually convert that into the binary version of floating point numbers. Okay, so right here, let's look at this part first. Okay, so this entire part, there are several components in it. In square bracket, it specifies what are the alternatives for a single character. So in this case, when I use open square bracket plus minus in a closed bracket, it basically means this character can be either a plus or a minus symbol, but nothing else. Okay, it's either a plus or a minus. But this character is followed by a backslash equal to. A backslash equal to is basically a quantifier of sorts. Okay, it's basically saying whatever is right before it can occur 0 or 1 time. Okay, the most common word to describe it is optional. So you have an optional sign that is the first thing of a scientific notation. Are we doing okay so far? What is after that is a backslash D. A backslash D, which is this part here, is indicating that this is a digit in base 10. In other words, it is a character from 0 to 9. It's basically the same thing as square bracket, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, close square bracket, because we are limiting this character to be one of the base 10 digits.
So backslash D is like limiting the backslash equals to, right?
Backslash D is the same exact thing as typing in brackets 0 through 9 bracket.
Yeah, well, this is a range. You can specify a range if right. So they yeah.
Yeah, so all you're looking for is a digit that is a numerical value between 0 and 9.
Yeah, exactly. All right, so what is it followed by? Well, it's followed by something that we have not encountered so far, which is a backslash open paren, and it has a matching close paren. So the question now is, what is that going to do? So this is the opening of a group. This is the close of the same group. What is inside the group? Inside the group, we have backslash period, which is actually a single dot. Okay, this literally just means the dot. Okay. And the reason why it's preceded by a backslash is the dot itself matches any single character. It is a wild card for a single character. But if I don't want to specify any character, I really just want that dot on the keyboard, I need a backslash to escape it. So backslash dot is just dot itself. And then it is followed by backslash D, which once again is 0 to 9, but it's only 1, okay? It's only 1, 0 to 9. So now we have an asterisk. Asterisk means whatever is right before the asterisk can occur any time. Can occur, 0 up to as many times as you want. So it is not the same thing as a backslash equal to, which is optional, 0 or 1 occurrence. This means any occurrence, okay? It can, including 0. Is that okay? And then the entire group itself, this entire group itself is also followed by a backslash equal to. Can someone tell me what that means?
It can happen 0 or 1 time.
But what can occur 0 or 1 time? The
The entire.
entire group.
Yeah.
Okay? In other words, the Mantissa does not need to have a point something. 5 is fine. 5 point is fine. 5.0 is fine. 5.0000 is fine. Are we doing okay so far? And we also have an optional sign before the entire thing. So plus 5.000 is okay. Negative 5.000 is okay. So are we still doing okay so far with this? Okay. What is after that? So after that, we also have a group. Backslash open paren opens the group. Backslash close paren closes the group. What is in the group? The first thing in the group is E, lowercase e, all by itself, which literally just matches lowercase e. And it is not followed by a quantifier, which means it has to be there. So the E has to be there if you want to specify the exponent. Yep.
Just curious, which flavor of regex is this? It's certainly not.
I think it's VI.
Okay, because this doesn't seem like Perl or JavaScript or.
Yeah, there are flavors of regex.
Yeah,
And this is the VI flavor.
Okay, because the only reason why I'm asking is because I'm used to curl, like
Mhm.
based ones, and like the equal sign and backslash, the excessive backslashes are pretty cool.
Yep. This is a VI version of a regular expression. Yep.
So to represent that, we have the slash d and the asterisk to represent the numbers after the decimal point, right? So why is it only one in the grouping?
Are you referring to this asterisk?
Yeah.
So this asterisk applies to this particular backslash d, which basically means you can have any number of digits after the decimal point, including 0. Yep.
It doesn't say that it has to be the same digit though, right?
It does not say it has to be the same digit. That is correct. Because each digit is basically the same thing as this, which means each digit only has to be one of the 10 characters, from the character 0 to the character 9. But they do not have to be the same.
And the E is 10, is basically a 10.
Right, the E is an indicator of whatever follows is the power of 10 that we want to specify. So the E, if you want to use the exponent portion of a scientific notation, then the lowercase e has to be here, has to be at this particular point. Whatever is following this is once again a plus minus, but it is also optional. So the sign of the exponent is optional. Is that okay? And then we are followed by backslash d again, but this time we have a backslash plus. So backslash d is basically once again 0 to 9, but the backslash plus means at least one of whatever is before that. So that means the exponent has to be in the form of e followed by an optional sign plus or minus, and then followed by at least one digit. Is that okay? Can you have 2 digits? Yeah, because it's at least one. Okay. And then the backslash equal to, that is right outside of the entire group, basically means this entire group here. Okay, let me start with the backslash. So that means basically this entire group itself is optional. If you want to just type in 3.14, it's good. If you want to type in 6e plus 5, that's okay too. Okay, so I mentioned that this particular regular expression format or syntax. Okay, so the syntax of regular expression can also be called a meta syntax because it is a syntax to describe a syntax. Is that making any sense? Sort of? No? Yep.
Is the period a literal period or is it the regex period?
The backslash period means the literal period.
Okay.
Because a single period is a special symbol to be in any character.
Right. The only reason why I'm wondering is because there's like backslash question. I just find this regex.
I think this one is VI regular expression because that's how I tested it.
Okay.
And then somebody's going to ask, what is VI and why do we need regular expression in VI? Okay.
VI is an editor.
VI is a text editor,
Yeah.
and why do we want to use regular expression in an editor? We can search for patterns. Very good. So if this is the actual pattern of scientific notation, then I can basically search for this and locate the numbers that fit the scientific notation in my program, which can come in pretty handy. Now VI can do regular expression not only in search, but also in replacement. So you can find something and you say, okay, when we search for something, we break it up into this chunk, and this chunk. And then when you replace, you can refer to the chunks that you have recognized earlier, so you can actually exchange orders of parameters if that is something that you need to do. So it's pretty cool, okay? The other thing that you might want to remember about regular expression, not going to be in a test in this class, but when you take it's either called automata theory or computational theory. When you take that class, regular expression has a special place in that class because it is the language that can be recognized by a finite state machine. And what is a finite state machine? Does anyone know what is a FSM or finite state machine? No? Does anyone know who's Alan Turing? Okay, so what was the contribution of Alan Turing? Yeah, he's some random guy in some random movie. Totally fictional.
Didn't he
Yeah.
crack the German Enigma machine?
Yes, he's the mathematician who
Yeah.
formed the basis of that, and he also designed a electromechanical computer that we talked about, the bomb machine, that was used to crack the Enigma encryption. So what does that have anything to do with finite state machines? No, so the whole theory of computational theory is Alan Turing's. Okay, and a finite state machine, as the name implies, is a machine that has finite states, as opposed to a non-deterministic. So there are different types of finite state machines, but the finite state machine has no memory. It only has its current state. So it can go from one state to another state based on the input symbol, but when it transitions in a state, it can also emit a symbol. Yep.
Is that the thing they draw out with like directed graphs and they say like, oh, it gets this character, it goes
Yep.
this way on the graph?
Yep. So if you have a finite state machine that has no memory devices whatsoever, the language that you can recognize is regular expression. Okay? And regular expression, even though it is really handy, it's really kind of useful, it is not that powerful. Because anything that has nesting cannot be recognized by a finite state machine. Anything that is nestable, which basically includes all practical programming languages, okay, cannot be recognized by a finite state machine. You will need to have a stack associated with a finite state machine, which is called a push-down acceptor or a push-down machine, in order to recognize anything that has nestable constructs. Question?
Kind of more of a comment, something that I kind of realized when I was, because I converted that syntactic when I understand a little bit better.
Mm-hmm.
And I know I keep going on about that, so I'm sorry. But something I did notice is that it only accepts one digit. I'm sure this is obvious to literally everyone else, but I figured I'd just point it out. It only accepts one digit before the period.
Yep.
So if you have 24 point blah blah blah,
It would not be recognized by
it
this.
wouldn't be recognized.
Scientific notation only has one before the period.
Right.
If it's normalized,
yeah.
right?
That's what I was trying to say. It accepts only normalized, which
Correct.
was important to mention, but I'm probably too dumb to be the only person.
No, that was a good observation. There's only one single digit to the left-hand side of the decimal point. Yep.
The plus behind the last D, that means that it has to have at least one, correct?
The plus, the backslash plus?
Yes.
Yes. So this particular backslash plus means, the backslash D that is right before it, you need to have at least one of those.
So why don't we have one of the first one?
This one here?
No, the very
Here,
first
this one? Yeah, you could have made it a backslash D and then a backslash plus if you wanted to make it that way. But then it wouldn't be
It
normalized.
wouldn't be normalized, and that's what I was trying to say, is that if we wanted to fix it, all we would need is a plus sign right there. And then
Backslash plus, yes.
Well, sorry, differences between regex. So.
Well, C actually does recognize just point something too, so you can make it an asterisk,
Yeah.
because you can have 0 digit prior to the
Oh, so
decimal
you
point.
could just have a point. You wouldn't need a 0.
You can have a point something, but you cannot have just a point by
Okay,
itself.
Yeah, so then it could be.
Yep.
Asterisk.
Yep.
So how do we get from the binary number to this version?
Well, the question is reversed. This is how we specify numbers in base 10. So the question is, how do we parse this first, okay? Figure out the base 10 version of the scientific notation, and then from there, we can try to convert the base 10 Mantissa combined with the base 10 exponent to the base 2 Mantissa and base 2 exponent. So the question is well understood, and it's a good question, except the direction is kind of opposite. All right. All right, so now the question is, how do you write a program to do this? You have an optional sign, followed by a single digit, followed by an optional part that has the fractional part of the Mantissa, and then followed by the optional part of the exponent, which consists of e, the lowercase e itself, an optional sign, and also a exponent that has to have at least one single digit. So how do you write a program like that?
Take it as a string first.
Okay, so let's assume that you already have a string, and and let's also assume that the number may or may not be well formed. In other words, if it has syntax errors, you have to say, okay, I cannot deal with this. It is not following the syntax. Yep.
You could like start by trying to break it into the chunks, right?
Yep.
Exponent, Mantissa, assign to.
Yep. All right. So I'm gonna leave that as a ungraded homework assignment. Now, if you don't have time, this one is not that important because it has more to do with parsing than it has to do with number representation. Okay. If you do have time, this is not a bad exercise to really just try to code something given the regular expression and then you. Okay, go ahead.
Wouldn't it be better to move the first bracket before the first digit, and then I'm only thinking because of what the capture groups are actually capturing, because the first capture group only captures Mantissa past the initial value.
Right.
So I don't know, I just think that
Well, the grouping is not for capturing. The grouping is more like for this quantifier to express whatever is before that is optional.
Okay, so those are non-capturing groups.
Yeah, these are not, well, it's not being used in a replacement context.
Okay.
So it may be capturing, but I don't really
Okay,
care
so
what is
capturing
capturing.
doesn't really matter. Okay.
Correct. It's just for grouping purposes because I just have to say whatever is before this is optional, whatever is before this is also optional. So that's why I have the grouping. Yeah, go ahead.
So like for the ungraded assignment, is it just to parse out the different parts of the number or to convert it as well?
Do not do the conversion, just capture it, okay? And the way I want to capture this is to express the Mantissa not as a fractional number, okay? So, I'll give you an actual example. Okay, and let me go to Tuesday, Thursday. There we go. Oh, same thing. Okay, where's my pen? Okay. So, in other words, if you're given with this particular pattern, let's say 3.25 e to -2, okay? So if this is the input, I want you to break it up so that the Mantissa, okay, Mantissa 10 is, I want that to be 325, not 3.25. The whole idea is I do not want this program to use floating point numbers or doubles whatsoever. All the processing, all the calculations should be done in integer math. Okay? So I want you to store the Mantissa in base 10 as 325 in this case, but that means the exponent in base 10 has to account for that shifting. So if the original base 10, if the original exponent for base 10 is -2, what should it be now? Now that I have bumped up the Mantissa to be 100 times of what it used to be, what do I need to do to counter that by adjusting the exponent? So e needs to be -4 because I need to add another -2 to counteract the multiplication by 100. Yep. That's what I want. Okay, so after you parse this particular string, I want a particular variable or a particular field inside the structure to hold Mantissa 10 to be 325. I want exponent 10 to be -4 because that would still be expressing the same value. No.
Why did it start with
Because 3.25 times 10 to the power of -2 is the same, or should be the same, as 325 times 10 to the power of -4. Because we're still representing the same value. We're just playing with, the exponent and the Mantissa so that we only need to represent integers. Is that okay? All right. So this is the other view of a floating point number. The floating point number is always having two parts. One part, which can be seen as this part, which is the Mantissa, which can also be seen as this part, which is the quantity of something. The second part is what is the unit, okay? This is the unit that we're expressing. So we are really specifying that we have 325 things. What is one thing? One thing is 10 to the power of negative 4. So when you combine these two, it becomes the actual value that we are representing. Now, of course, this is all in base 10, but the idea in base 2 is really the same. You have a quantity, and then you have a unit. The unit in base 10 can only be a power of 10. The unit in base 2 can only be a power of 2. Is that okay so far? I'm hoping this will tie into the lab of the early lab. Is it working okay a little bit? It's not doing what it's supposed to?
I can see where it's going.
Sorry?
I can see where it's going.
Okay, very good. Okay, so are we okay with this part? You know, how to parse the number and how I want the values of the Mantissa and also the exponent to be represented. Okay, yep.
So the ungraded assignment would literally just take some scientific notation.
Yeah,
number
as a string.
As a string, of course, from console input, and then just give you that, just give you the 325
Yep.
and then exponent.
Yep, well, and the sign, but the sign is not really that important. Just break it up and put it into two different members, and one member is going to be the Mantissa, the other member is going to be the exponent. Yep.
Is the optional assignment going to have its own outline on the modules?
It doesn't really have
Or
it.
is this just what you're saying?
Yeah, it's just what I'm saying, because however you want to do it, like you can read it from standard in. You can also read it as an argument to the executable. Either way is fine. Whatever you do, just try not to hard code it, because if you hard code it, it becomes really hard to test, different numbers.
And if we're like, let's say reading it as a string, is the string going to be all? Is it all going to be digits, or might there be like a period somewhere in that and how to account for
This
that?
is a typical thing in a string. So that string will include the ASCII code of 3, the ASCII code of a period, the ASCII code of 2, the ASCII code of 5, the ASCII code of lowercase e, the ASCII code of minus, and the ASCII code of 2, and then followed by a null terminator. So that will be the content of the string. Yep.
Should we handle garbage input or just
Should we?
handle garbage input or just?
You should probably stop the parsing once you understand. Okay, this is not expected. You should stop parsing right there. So instead of handling garbage as if it's not there, you should just kind of stop and go like, oh, this is no good. You can just abort the entire parsing. So in C++, you can just throw an exception, so that you can catch it in main and go like, okay, that number is no good. All right. So are there any questions about what I want you to do, for the optional ungraded assignment? So once again, if you don't have time, this is not the crucial one. Okay. So there's another one that is even more important. So if you don't have time, I would save time for the next one, for the whatever is following this one, which is the actual conversion. All right? Okay. So any additional questions about the parsing of a base 10 scientific notation? Questions? All right. So if there's no question about this, I'm going to start with the conversion of a specific scientific notation that is already quote-unquote parsed. Okay? So I'll give you something like this. Okay, so we have, let's say, 25 e negative 30. Okay, so this is a really, really small number. Now, how do you change this to become a base 2 floating point number? How do you change this so that we end up with a double precision floating point number? That becomes the question. Yes?
Real fast before we get to that, I noticed this isn't in scientific notation.
Fine. The parser would choke on this one because we know we want just one digit ahead of before the period. Okay, so we have a dot here. Okay, so the first thing we want to do is to parse this into a integer or unsigned integer Mantissa, and then adjust the exponent accordingly. Okay, So I'm going to use M10 to mean Mantissa in base 10. So that's going to be 25. And then E10, which is the exponent of base 10, is not negative 30 anymore because I just bumped up, okay, the Mantissa to be 10 times of what it should be. So in order to adjust for that with the exponent has to decrement by 1. So my actual exponent in base 10 should be negative 31. Is that okay? All right. So the value represented by this whole thing is M10 times 10 to the power of E10, right? And I want to somehow change this, okay? So through some process here, I want this to become some M2, I don't know what it would look like at this point, times 2 to the power of some E2, and once again, I have no idea what the E2 is supposed to be, but this is the objective. This is the whole conversion process. Is that making any sense? Yep.
Can you repeat how we got negative 30?
Because I turned the 2.5 into 25.
Okay, I thought it was
So it's
25.
10 times what it used to be. So I need to somehow adjust for that. So I need to divide it by 10 again. But instead of dividing it by 10, I'm just subtracting 1 from the exponent.
Looks like a 25. That's
Yeah.
Oh, you cannot see the dot?
No.
Okay.
There we go.
Bigger now. Okay. So this is the objective. So how do we get this done? Now, if the exponent is not something absurd like negative 31, if it is something more reasonable like 5, it's easy, right? Because if E10 is 5, all we have to do is to say, oh, so it's 25 times 100,000, which is an integer, right? And then we just need to go through base conversion, and we're done. Because no one says E2 cannot be a 0. If E2 is a 0, then we don't have this term here. So if M2 can be an integer, then we're all done already. So I picked this particular example because we cannot use that trick. It's not an easy one. So if it's not an easy one, what are we going to do about it? Well, we have to do it step by step. Okay, there's no magical way to do it all in one shot. So, and remember, we want to only use integer math. Okay, we don't want to use log. We don't want to use power. We don't want to use anything that requires double or floating point. Is that okay? All right. So eventually, what we want to do is to get rid of E10. In other words, we want to make E10 gradually become 0. But in that process, we'll also start to have an E2, which is starting from 0, and then go on the negative side until we have something that represents about the same value. Is that okay? All right. So how do we change E10 from negative 31 to, let's just say, negative 30? I have to divide the Mantissa by 10, don't I? Because if I increment the exponent of base 10, I have to cancel out that operation by doing something with the Mantissa. But dividing 25 by 10 as an integer division has a problem. What kind of problem do you think that is? We have truncation. Okay, so if you have 25 and you divide it by 10, conceptually to us there's no problem. We just say it's 2.5, which is exact. That's the correct answer. But when you divide 25 as an integer by 10, which is also an integer in C and C++, it becomes an integer division. And in an integer division, the fractional part is truncated, it's lost. So instead of having 2.5, you have 2. That's not acceptable. Why is it not acceptable? You lose a lot of precision. How much are we talking about? 2.5 versus 2, okay? 2.5 is the actual value, and 2 is what we ended up with. So the difference is 0.5. It's 0.5 out of 2.5, which means our accuracy is really poor. We lost 20% of the value. And that's right out of the gate too. That is not good. Okay? Because Elon Musk's, roadster is not going to end up on the Mars, orbit. It's going to end up in the sun. I guess that's going to be a really bad pun because Elon Musk also owns a solar city. So here's all the solar energy that you can use to power up your roaster. Okay, geek joke. So that's not good. So how do we fix that problem? How do we minimize the loss of accuracy? Yep.
Modulus first.
Say again?
Use the modulus first.
Modulus? That's not going to help us, unfortunately, in this case. Yep.
Round.
We can round, but rounding doesn't fix the problem because we can round it up to 3, right? Instead of 2, you have 3. And 3 is still 0.5 off from the expected answer of 2.5. So you still end up with 20% of error, except it's in the opposite direction. So that doesn't fix the problem either. How do we fix the problem? Let's try something like this. Okay, so I'm going to erase what I just wrote here, and then we'll say, okay, we have 25 to begin with. Let's multiply by 2. Okay, in other words, I'm re-expressing my number. Okay, let me go back and explain what I'm doing. Okay, so my number currently is 25 times 10 to the power of negative 31. I want this to be something times 10 to the power of 30. Okay, but I don't want to lose precision. Is that okay? So I still need to do a division by 10. But the problem is, if I divide 25 by 10, I lose a lot of precision. What if I divide 50 by 10? If I divide 50 by 10, that turns out to be perfect, right? Okay, but that's just because of the number that I chose to use. Okay, so let's choose something that is not going to work out nearly as well. Okay, make this 2.3. Okay, so now we have 23 instead of 25. I multiply 23 by 2, we have 46, right? 46 divided by 10, if you do an integer division, what kind of percentage am I losing? Is it about the same? I would say about the same. Because 23 divided by 10 is 2.3, okay? And we lose the 0.3, so that's about what? It's 3.3 out of 20, which is 15% of error. Okay, that's 15% of error. If I use 46, okay, so let me just write down what I'm doing here. Would anyone argue that these two are the same? Okay, they're the same. So instead of writing it this way, okay, can I write this as 46 times 10 to the power of negative 1 times 2 to the power of negative 1? Okay, that's cool. So this is how we get to start with E2 and make it non-zero. Okay? And look at this number and go like, okay, 46 divided by 10 should be 4.6. But because of the truncation of integer division, we're losing the 0.6. So we still end up with a 30% error rate, which is, hey, it's not helping. 15%, sorry, 15% of error. It's still not helping. Okay, let's bump it up again. 46 times 2. Huh?
Could you do it in a way where you have 2.3, right? And could you multiply it by, say, times, not 10, but actually 100, and then divide that by 10 all the time?
But that's not going to help. You want to multiply it to make it bigger, but not by any power of 10. You only want to multiply by powers of 2, but you divide it by 10. Okay? So we're going to bump it up again. So this time we bump it up by 2x it again, or twice the number, twice the value again. What is 46 times 2? 92, okay. So can I write it like this? It's okay, it's a tough book. It can survive that. Okay, so can I write it like this? Because I'm just using this to account for another doubling of that Mantissa. Right? Okay. If I divide 92 by 10 now, what is the kind of error rate that I'm getting? It will be 2 out of 90, right? Or 0.2 out of 9. That's smaller, right? We are getting down to about 2-3%, right? So if I continue with this process, how far should I go and how far can I go? Okay, that's the next question. So what is 92 times 2? 184, okay? So can I write this as 184 times 10 to the power of -1 times 2 to the power of -3? Absolutely. So now the question is, how far do I want to take this before I actually do the division by 10? Because I am really minimizing the error now. Okay? Okay, I'll do one more step and then I'll give you the actual answer, okay? So we multiply by 2 one more time, so we have 368, okay? 368 times 10 to the power of 31, -31 times 2 to the power of -4. And this time I think we still have the same loss. Multiply this by 2 again. Okay, so we can keep doing this. Yep.
So, I mean, like, this is probably evident, but we're never going to get to a point where it's going to be an equal or an even divide. So, what's I guess probably...
It will never be an even divide. There's no way it can be an even divide because we are divided by 10, and 10 has 5 as a factor, and whatever's on the top has no factor of 5. It did not start with 1, and it will never have 1 because we keep multiplying it by 2, and 2 is not a factor of 5. 5 is quite something. So we'll always end up with a loss. The question is, how far can I take this before I go like, okay, this is good enough? Okay? Yep. Aha, okay, I like that answer. We'll keep doing this until we run out of bits. Okay, so let's say we're dealing with a 64-bit processor, which means the natural width of integers is 64-bit. Okay, so now the question is, what is the largest number that I can take this that is still less than or equal to the extreme of what a 64-bit unsigned integer can represent?
2 to the power of 53 minus 1.
2 to the power of 53, well, 64. We're dealing with the entire 64-bit number now.
Okay, so
yeah.
63.
Okay. Well, okay, but what is the quickest way to figure that out? Okay, so I'll give you guys a trick. Okay, so I'm going to open a new slide, and we'll get back to this one. 23 as a base 10 number is what in binary? In base 2. So in base 2 is 116, right? 16 plus 7. So there's no 8, and then 111. Is that okay? Okay, so that's the binary representation. So what I'm really asking is how many zeros can I add on to the right-hand side until I run out of digits? That is the question.
6.
No. There are 5 bits here already. If your integers can only have 64 bits, that means we can add 59 zeros. Okay? So am I going to write 59 zeros? No. So how am I going to represent that quantity in a class like this? No, I got something better. Left shift 59 bits. Okay, so this is also a good time to kind of pause and make sure that everybody understands what is left shifting. Are you guys okay, comfortable with the bit shifting operators, or you have never been introduced or exposed to bit shifting?
It was in one of the labs that we were doing, one of the links that was talking about
Yep.
one of the links that was in the lab was what was in it covered the shifting.
Yep. So are we okay with this? Yep, go ahead.
In this case, it'd just be multiplying by like 2 to the 59.
That is correct. It is equivalent to multiplying by 2 to the power of 59. Yep. But the reason why I use bit shifting is because it is not a power function, and 2, it is a very inexpensive operation. Almost every commercial processor can do bit shifting in one single clock, which means this doesn't take any time at all. Yep.
So every time we got 46, 92, 182, it was really the same binary, just shifted to the left one.
Yep. So this is going to be a pretty big number, okay? But when we get to this point, what are we going to do with the other stuff? In other words, let me go back to the previous slide. So now that we know what it looks like, what is this number going to look like when we change this so that we have here, we have 23 shifted to the left-hand side 59 times 10 to the power of -1, times 2 to the power of what? Okay, so this is shifting by 1, we adjust by 1, shifting by twice, shifting twice, we adjust by 2, shifting 3 times, we adjust by -3, shifting 59 times means it's 2 to the power of what? -59. How many times you shift in here is how many times you have to adjust by decrementing the power of 2. Are we doing okay so far? Yep.
How did we get to the 59?
Huh?
How did we get to the 59?
Because 23 has a bit pattern that needs to use exactly 5 bits.
Okay, so it's 64 minus.
Yep, 64 minus 5 is 59, so we need to pad 59 zeros, and every time you shift ones to the left, you're padding 1 0. So we have to shift in 59 zeros in order to fill in the entire thing. Yep.
Just kind of speaking programmatically, so we would have to first convert the Mantissa to binary, and then just see how many that was, 64 minus that.
You convert the Mantissa to an integer.
Oh, yeah.
Just an integer.
Yeah.
Yep. Now this is working for in the case when the exponent of 10 is negative. Okay, when it's positive, it works out a little bit differently. Okay, so are we okay with this representation so far? Okay, can I do a division by 10 now?
Yeah.
Okay, and what kind of accuracy am I going to get? What kind of error are we going to get? There will still be an error, right? But it's going to be pretty small. Okay, so I'm just going to write it here. Okay, so we'll say, okay, after we do all this shifting, let's divide it by 10. Okay, and then we say, oh, if we are dividing this by 10, then we can adjust the exponent of 10 up by 1. We can increment by 1 because we are moving the division to the other side. Is that okay? Sort of. Not really exactly okay, but getting closer. Yep.
You dropped the negative on the power third.
Oh, okay. But this is only sort of okay. It's not exactly okay. And the reason is because when we do an integer division, we're still truncating. In other words, the actual result of this integer division is always smaller than what it is supposed to be. Okay? And if we do this many, many times in the whole process of conversion, and every single time we divide, we're losing something, that means the actual result is going to be a little bit smaller, okay? It's going to have a negative, it's going to have a bias to one side of rounding. Because we are not rounding, we are actually just truncating. So instead of truncating, I would like to do rounding, okay? So that opens up another slide to talk about rounding and how we can do rounding without using floating point or double precision math, okay? So is it okay for me to leave it here as it is now, and we're just gonna click on a hyperlink and then we'll come back to this later? Okay, yep.
For the round, do you mean like every single time you divide by 10, or do you mean like
every single time we divide by 10, we want to do rounding. Yep.
Just for clarification.
Yep.
What is the reason we're trying to eliminate error for truncation? Is this part of removing our Mantissa from base 10 to base 2, or is it just to cover issues when dividing?
It is a general issue of division, because when you're using integer division, it is always truncating. Which means if you have successive operations and they're all doing division, each time you're losing something, so whatever the result is a little bit smaller than what it is supposed to be. But if each time you err on the same side, that means it becomes cumulative. So at the end, what you end up with is going to be a value that is significantly smaller than what it is supposed to be. Okay? And that's why rounding is good, because rounding is not making up for precision. But it is saying, okay, sometimes whatever you end up representing is a little bit smaller, but other times it's a little bit bigger. So it kind of averages out so that you don't have a particular bias to one side or the other. Okay? Yep.
Can I see the slide that explained the shifting?
That would be the next slide. You mean this one?
Yeah.
Mm-hmm. Well, in fact, I can just use this slide to talk about rounding. Okay. So rounding is not really a particular new idea, I hope not to this class. If you round anything that has a fractional part that is at least 0.5, you bump it up to the next integer value, right? Okay, so this is 2. If the fractional part is less than 0.5, then you round it down to the smaller integer value. Is that okay? So there's a round function, I'm pretty sure, in the floating point library, but I don't want to use any floating point math. That's the whole point. So how do I do rounding, but without using the floating point math? Yep.
The modulus.
The modulus.
Yeah, you check to see, since it's base 10, you just say if that number modulus 10 is greater than or equal to 5, do the division, and then add 1.
Well, not quite there yet. Okay, so the first thing we'll do is we will take a look at rounding and say, can we do rounding without using round but use floor instead? We like floor because floor is free when you do integer division. Okay, truncation is free. Is that okay? So now I'm asking, can I express the round of x? Okay, whatever x is, okay? Can I express it as the floor? This is the floor, symbol. So the floor is basically returning an integer that is as large as it can be, but still less than or equal to x. Okay? That's taking the floor function of something. So the question is, can I convert round to floor? And the answer is yes. Okay? So it's just x plus 0.2, 1/2. So if you take the floor of x plus 1/2, it is the same thing as rounding. Okay, but this is not helping because we cannot represent 1/2 as an integer. Well, that's absolutely true. But there's one thing that is on our side. I only need to do rounding when we are doing division. Let me say that one more time. We only lose something. We only need to do rounding in order to make sure whatever we lose is not only in one direction when we are doing division. Okay, all right. In fact, in this case, we're always dividing by 10, okay, when we're dealing with this scenario. how is that going to help me? So we say, okay, we are always doing division. So whatever we are rounding is some number x divided by 10. Okay. So we can just plug in this whole thing and it becomes that. Yes? We still have that 0.5, don't we? Not anymore. The 0.5 goes away. And you go like, but that division is still a floating point division, and then we take the floor. If you use integer division, it is automatically flooring. In other words, if I use only integer operators, this is nothing more than just adding 5, the integer, to x, which is another integer, divide the whole thing, the sum, which is an integer, by 10, an integer. So now, I've converted everything to just integer math, or integer operations. Is that okay? All right? Okay. So I'm going to plug this back to whatever we had earlier. Okay. So we'll scroll back to the previous page, which is right here. And this time we just have to remember to add the 5 first, for rounding purposes. Is that okay? So you carry out this math here. Yep.
So like with the 23 shift left 59 plus 5, like is the 5 being added to the whole result of that?
The 5 is added to the shifting before the division. No. So it is 23 left shifted 59 times, which is an integer, really big, plus 5 to that really big integer, and then you divide it by 10. Are we still going to lose something? Absolutely, but it's going to be small. And on top of that, every time you perform this kind of operation, which way your error is, sometimes half the time it's going to go into this in this direction, half of the time it's going to go in the opposite direction. So you no longer has a consistent bias when you are when you have errors. Yep.
We had 5 every time we divide by 10.
Yep.
So then it would be, if you want to do 10 to the 31, it should be 5 to the 31.
Say that one more time.
So if you wanted to,
you mean this one here?
yes. Well,
that's implicit.
okay.
Yeah, that part is implicit. Yep.
So like the point of adding 5 is just so that when the truncation actually happens, that it weights it to work like a round.
Yes, absolutely. That's exactly what the plus 5 is. Are we still doing okay so far with this math? Shall we actually go ahead and do this? Now, I found out one thing that's really interesting. When you perform math like this magnitude in spreadsheets, especially, they don't represent the actual value exactly anymore. In other words, spreadsheets are actually internally using some kind of floating point representation. So because how wide is the Mantissa again? In a double precision floating point number? 53 bits, effectively 53 bits. Okay. So that means if you try to represent any integers that have more than 53 bits, it's not going to be represented exactly anymore. Which is a problem, because now, what do we do with this? Well, fortunately, I have a command line. We still have GDB. This is still the same GDB session that I think we left open the other time. So we can just do this, okay? So we can say what is, now when you do this, you have to be careful when you use GDB, because 23 has a type of integer. Unfortunately, GDB understands the integer type to be 32-bit only. So 32 is not going to work the way we think it should work. So the best way to do it is really to typecast 23 first to 64-bit unsigned. Then you can do the shifting, because otherwise it's not going to work. Okay, so we shift it by 53 times, and then we add 5 to the whole thing, right? And then we divide 10 from this entire thing. Okay, so that turns out to be this number. Is that okay? Yep.
So the 64 bits are all usable as many bits for like the exponent stuff?
Let me switch back here. So this portion eventually will become the power of 2 in the base 2 scientific notation. What our objective is gradually get rid of this 30, negative 30.
I'm just saying, because like, doesn't the representation have to contain like the positive and negative?
Positive or negative for which part?
The format of the number. It's not.
The value itself? You mean the sign of the entire floating point number?
Yeah.
Yeah, but that's not really important, right? I mean, because that's just one single bit controlling the sign of the entire value. So we don't worry about that when we're conversion. Because when you're converting from base 10 to base 2, are you changing the sign? Or do you preserve the sign regardless of the base? The sign is preserved. So I'm not really that concerned about the sign itself. Okay? Yep.
Is it true that using only integer operations, that the more decimal places our scientific notation number has, the less precisely we can represent it? So say you're given, 1.145, 10 numbers.
For 10 digits after the decimal point.
So when we convert that into a Mantissa, that's going to be like a couple, like 10 billion or something, right?
Yeah.
In integer.
Yeah.
So then we would only actually be able to bit shift that like a few places.
No, we can shift a lot. Because 52 or 53 bits actually gives you the ability to represent in base 10 up to about 18 digits.
Oh, okay.
So we are actually okay in terms of precision. Yep, there was another hand. Yep, go ahead.
Right, so just so I'm double checking, the 2 to the negative 59. The reason why we have 59 is because we're already using 5 bits.
Right.
5, okay, just double checking.
We are already using 5 bits, but we want to build up 64.
Right.
So we need to shift in 59 zeros to the right-hand side of the original representation of 23. Yep.
Why not like something that would add it together, give us like 53 or whatever?
53. Because we are not even close to done yet.
Okay, so if we were trying to fit it in those bits.
Because right now we have moved our base 10 exponent one step closer to 0. Is that okay? All right. So let me see if I can do this. Let me see if I can copy and paste this number into the tablet. So copy. And then the paste is going to be tricky because I need to know whether it can let me type something. Looks like I can type something because that looks like a keyboard to me. But where do I? Oh, there we go. Oh, but it's not on the same device. Okay, so that is not going to work. Okay, turn off the keyboard then. Turn back. Go back to the pencil tool. Oh, this is going to be. This is not going to be. Okay, that would work. And then go back here. And then on the other side, where's my pen? Right there. Okay. Okay, you guys can see the equal, right?
Yeah.
1 3 2 5 8 5 9 7 3 0 2 9 8 7 4 0 2 2. Huh? Close enough. Okay. Times 10 to the power of negative 31. 30. Okay, we got rid of 1. Times 2 to the power of negative 59. Okay. Scroll up. Now we repeat this whole process. In other words, oops, okay. Gotta go back here. Okay, so now the question is this number, even though it is really big, is it as big as it possibly can before I do another division by 10? How can you tell?
If it's greater than, or if it's equal to 2 to the power or 64.
So how do you make a loop? Okay, how do you make a loop? Given a particular unsigned 64-bit unsigned number, how do you say, okay, I'm going to shift it again if it is not as large as it possibly can? How do you know you have already made this number as large as you possibly can and do not shift it any further? Check for overflow, but there's no overflow. That's the best part about C is you can overflow your integers and it doesn't tell you. So how do you know? Yep. Yeah, go ahead.
Okay. If the variable is greater than itself times 2.
Okay. Say that one more time.
If the variable is greater than itself times 2.
The variable is greater than itself times 2. That is not a reliable way to check. Because when it overflows, there's a chance that the overflow representation turns out to have a bit pattern that is greater than the original bit pattern.
Okay.
That's possible. So it's not a reliable way. But there's an easier check. There's a very, very easy way to check and say that, yep, we have shifted enough, let's stop. Yep.
No, like, I don't know if it is a thing, but why would there not be like some sort of thing that would just tell you if it was like a function or a flag?
There's a flag per se, but it's not exactly a flag. Yep, there's one more hand.
Subtract 2 to the 64th.
No, you don't need any subtraction. Okay, should I disclose the answer? You check bit 63 of the value. If bit 63 is a 0, that means we have room to shift. If bit 63 is a 1 already, we don't have any room, stop. Is that not making any sense? Yep.
You check it with like a bitwise operation or
Yep.
something?
Yep, you do it with a bitwise AND operation. And then whatever the result of the bitwise AND is, reflects just that one bit. Okay? All right, so the way to do it, okay, I can do it in GDB. Okay, so I'm going to look at this number, okay, and I can say just $7. So this is the really cool part of GDB is you can refer to an earlier computation result just by referring to the dollar and then the number. So this way I don't have to copy and paste and redo the calculation and stuff like that. So I can do a bitwise operation. Now if I really want to be sure, okay, I can say do the typecasting again, because sometimes I'm not really sure and it's just good to typecast again. So now I can bitwise AND with UN64_T 1. Really, do we need to cast 1? And the answer is yes, okay? I'll show you what happens when you do not cast it. Then we shift it how many times? We're trying to look for the most significant bit, which means we have to shift it how many times? Every time you shift, when you shift once, you introduce 1 0 to the right-hand side. So how many times do I need to shift? 63 times. Because the number has 64 bits. The 1 is taking up 1 bit. We need 63 zeros to the right-hand side to fill up the entire thing. So it's 63. We have room to shift. How much room do we have to shift? Well, we can always change this one. Now that we know bit 63 is a 0, 62 is also a 0. We can shift at least twice. 3 times. And okay, so we can shift 3 times. So usually it is going to range between 3 and 4 times. Why do you think that is the case? Okay, the value itself before the division by 10 is as much as it possibly can, and it fills up all 64 bits, right? What happens when you divide something by 10? The number gets smaller, right? But it will require fewer bits to represent it. So division by 10 is somewhere between division by 8 and division by 16, isn't it? because 10 is between 8 and 16. Division by 8 is shifting, is getting rid of 3 zeros, getting rid of 3 bits. Division by 16 is getting rid of 4 bits. So when you do a division by 10, depending on what the numerator really is, sometimes it will clear up 3 bits, other times it will clear up 4 bits. But it's between 3 and 4, it's one or the other. Yep?
Can you explain one more time what's going on with the single and the bit shifting?
Okay, so the single AND is what we call bitwise AND, which is also the same thing as what you do with a multi-bit gate. So this operation here, not counting the shifting, okay, so if you look at the shifted result as one thing, this is X, this is Y, this is a multi-bit AND gate. It is a 64-bit AND gate in logic sim, which you cannot have. Yep.
Why do we want to divide by 10 again? So we divided by 10 the first time too.
We divide by 10 because we want the exponent of 10 to go from negative 31 all the way back to all the way to 0.
Okay, so this is the answer to the question I had in the lab, isn't it?
Yes.
Okay.
It is related. Yep.
That kind of didn't like fully answer my question. So the bitwise AND is checking it bit for bit, right?
Yes.
Okay, and then so what is happening with the bit shifting?
The bit shifting, okay, so one is just 0, 0, 0, 0, 0 all the way, and then the least significant bit of bit 0 is a 1. I don't want a bitwise AND with bit 0. That's not what I'm checking. I really need to check whether the most significant bit is a 1 or not. Because if the most significant bit is not a 1, I got room to shift one more time. And then I go back to the loop. Do I have room? Yes. Shift it one more time. Do I have room? Yes. Shift it again. In other words, I want to fill up all 64 bits before I do a division by 10. But how do I know that I have filled up all 64 bits? I look at the most significant bit. If the most significant bit is a 0, that means I have not filled up the entire 64-bit number yet.
So that bitwise AND is going to return bit 1.
You mean this one?
No, the bitwise
This one?
AND with S7 and 1, that's going to return bit 1.
No, that's going to return.
This one?
No,
I'm
so
not understanding how
before the
it's
shift. So basically what he's trying to do is he's trying to make sure that everything, that we have room to shift, right?
I get that.
Okay, so when you do an AND between the 64-bit number and the 64-bit number, we're making sure that it's not 1, right? Because
We're checking, we're trying to see whether it is a 1 or not.
Yeah. So we're making sure that it's not a 1 by doing an AND gate on all 64, and then we're shifting over so we're only getting result for bit 63. So that's how we're checking that we have room to shift.
Okay, so let me answer a few other questions first, and then we can come back to this one. Yep.
I'm curious how the division would work with the binary 23 divided by 10.
Well, what do you think? What do you think that's going to be?
Or I mean, like, how you would do it in, like, the way that we added binary numbers and subtracted binary numbers, but how would you divide them?
Well, you asked me, you wonder what the binary division is between 23 and 10, and it's just going to give you 2 because it's truncated. Because it should be 2.3, right? But it's because it's an integer division, you only keep the quotient part, you lose the fractional part. And the quotient part really is just 2.
But I mean, like, if you were to divide 10111 by 1010, how would you do that?
Oh, you mean how do we actually do division by 2, in terms of operations? We can talk about that, but not today. So today we just want to focus on bit shifting and floating point number representation. Yep.
So just double check. When we do 1, 3, 2, blah, 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 and then divide by 10, we would move over 3 bits, right? Since it's between 8 and 8 and 16.
Okay, so the other way to look at this is to look at this in this way. So let me, time already. Okay, so we can look at this as a hexadecimal number because that is also kind of easy to look at because we don't have to count zeros, right? So this one is the most significant hexadecimal digit. And we know the most significant, we know one hexadecimal digit is represented 4 bits.
Yeah.
So 1 as a hexadecimal digit is represented by 0, 0, 0, 1.
Right.
So this is the other way that we can actually quote unquote visualize that the most significant 3 bits are all zeros.
Right. So we can still divide by 10 one more time at least. Yes.
We can, but if you divide this by itself by 10, then you're not minimizing the error anymore. If you shift it 3 times and then divide it by 10, then you are minimizing the amount of error that you get out of that division. Because the ratio of error when you perform integer division has to do with the ratio of your numerator versus the denominator. In our case, the denominator is always 10.
Oh, so we just need to shift it over.
We always want to maximize the numerator as much as we can in order to minimize the error. Yep.
So we keep shifting it and dividing by 10 until that power of 10 gets to like 0.
Exactly. Yep. But every time you do something like this, every time you shift, you have to adjust the power of 2. So that power of 2 is going to get smaller and smaller and smaller. Right now it's negative 59 already, right? It's going to get smaller and smaller because every time we want to minimize the error of division by 10, we want to bump this up. But when we bump up the Mantissa, we have to adjust the power of 2 exponent. So that's why, every single time you do a division, you have to shift 3 or 4 times before you can do a division by 10, and then you do the whole process again. So you keep doing this until your base 10 exponent goes from negative 31 to negative 30 to negative 29 to negative 28 all the way to 0. By the time it gets to 0, then you have your binary floating point number, almost. Because you're expressing a quantity times a power of 2. You don't have powers of 10 anymore. Well, you do because it's 10 to the power of 0, which is not going to bother us. Yep.
So like the only thing introduced in here is that division by 10. Right?
Yes.
Like if we used a different base in our writing and stuff like that, a base that was divisible by 2, then this whole process could be error-free, right?
If you're dividing by 2, which is the same thing as shifting to the right-hand side, you can still lose something. Okay. So we'll talk about this next time. Is what happens when your exponent of 10 is really big, like 30. What are you going to do? Because you only have 53 bits to represent the quantity, and that can only go up to 1.8 times 10 to the power of 18 or so. So but once you exceed that, you're going to lose something. So you will still end up with a precision issue because you're going to be shifting zeros and ones out of the number. So you still need to do rounding even when you're dividing by 2. Yep. All right. So let's go ahead and go to the lab. Let me power down all of this stuff first.